Hello dear students, all of you welcome to Vidyan classes. It is the fifth lecture on relations and functions. Today we will discuss important memory tips in lecture number 4, problem discussion on partition of a set and equivalence class. Lastly, we will discuss congruence motor relation on integers. First, important memory tips in lecture number 4. Partition of a set. What is partition? In the previous class, we have discussed partition of a set. Let A not equal to phi. P is the set of P1, P2, Pn. Be the set of all non-empty subsets of capital A. Let A not equal to phi. That means A is a non-empty set. P is the set of all non-empty subsets of A. P is called partition of A if first condition I varies 1 to n, Pi that is equal to A. Union of all subsets of A is equal to A. Second condition, Pi intersection Pj is equal to phi. Union I varies 1 to n, Pi is equal to A, intersection of Pi intersection Pj is equal to phi. That means intersection of any two subsets of A is a null set, where I varies I not equal to j. I not, where I varies 1, 2, 3 up to n, j varies 1, 2, 3 up to n. I not equal to j. I varies 1 to n and j varies 1 to n, but I not equal to j. Clear? If these two conditions are satisfied, then P is called the partition of A. Clear? Equivalence class. What is equivalence class? Let A belongs to small a belongs to capital A and R is the equivalence relation on A equivalence class of A is written as bracket of A or bracket of A R is the equivalency relation which is same as is the set of X and defined by equivalent class of A which is same as equivalent class A for the equivalency relation R is the collection of X so that AX belongs to R, where R is the equivalence relation. It is the definition of equivalent class. Let A belongs to capital A and R is the equivalence relation on A. Equivalence class of A is written as bracket of A or bracket of A for R and defined by equivalent class of A is the set of X so that A and X are related where R is the equivalence relation on A. Last class we have discussed partition and equivalence relation. It is the definition of a partition and it is the definition of a equivalence class. Properties. Of equivalence class. What are the properties? Let AB belongs to capital A. First properties, A belongs to equivalent class of A. It is the first property. A is the element of A, capital A. Bracket of A is the equivalent class of A. It is satisfies A belongs to equivalent class of A. Second property, equivalent class of A is equal to equivalent class of B. Implied and implied by A related to B. A related to if two equivalent classes are same, that is equivalent class of A is equal to equivalent class of B. A and B are related. The relation is the equivalence relation. Third property, the equivalence relation are decomposes or partition the given set into disjoint. The equivalence relation capital R decomposes or partitions the given set into disjoint equivalence classes. That is equivalent class of A intersection equivalent class of B is equal to 5, or equivalent class of A is equal to equivalent class of B. Two equivalent classes are identical to each other or disjunct to each other, and equivalent class of A union equivalent class of B is equal to given set A. Equivalency relation are decomposes or partitions the given set into the here the given set is capital A into disjunct equivalent classes. Two equivalent classes are identical to each other or disjunct to each other. Union of all equivalent classes is equal to set A. The union is A set and the intersection is phi if two equivalent classes are disjoint to each other or identical to each other. These are the memory tips of lecture number 4. So that we will continue lecture number 5. Note down. First question. Find the number of equivalence relations on capital X. Capital X is the set containing 1, 2, 3. By the properties of equivalence class, each equivalence relation decomposes or partitions of a given set into disjoint equivalence classes. In other words, we can say each partition gives an equivalence relation. What are the partitions of X? Solution: X is equal to set of 1, 2, 3. Is a partition of X. Since union of this set and this set is X, and the intersection of any two sets is phi set. It is the condition for partition. Is a partition of X. Since union of this set and this set is X and intersection of this and this is phi. Similarly, it is a partition of X. It is also a partition of S. And set of 1, 2, 3 are the partitions of capital X. 1, 2, 5 are the partitions of X. Each partition produces an equivalence relation. The number of of the number of partitions of X is the number of partitions of X is 5. Implies the number of equivalence relations on X is since each partition gives an partition, since each partition of a set gives an equivalence relation. The number of partitions of X is 5. That implies number of equivalence relations on X is 5. Since each partition of a set gives an equivalence relation, therefore the number of equivalence relation, number of relations is 5. Answer. Clear? These are the partitions of X. The number of partitions of X is 5. That implies number of equivalence relations on X is 5. Since each partition of a set gives an equivalence relation, therefore the number of equivalence relations on X is 5. Clear? The number of equivalence relations on X is 5. Clear? Okay. Note down. Next question. Let capital R be the relation on the set capital R of real numbers so that A related to B if and only if A minus B is an integer. Test whether R is an equivalence relation. If so, find the equivalence class of 1.5 with respect to this equivalence relation. Here it is given by R is the relation on the real set such that A related to B if and only if A minus B is an integer. We have to test R is an equivalence relation. If R is an equivalence relation, then we have to find the equivalence class of 1.5. Here it is given by R is the relation on capital R, that is real set, defined by A related to B if and only if A minus B is an integer. Clear? R is the relation on R defined by A related to B if and only if A minus B is an integer. Or we can say, or AB belongs to, AB order pair belongs to R implies and implied by A minus B is an integer. First we have to test R is an equivalency relation or not. R is an equivalency relation. That means R satisfies the definition of reflexive, symmetric and transitive. Test for reflexive. For all A belongs to capital R, that is the real set. A minus A is equal to 0 belongs to Z set. That means set of integers. Is true. That implies A order pair belongs to R. That is, for all A belongs to real set, A order pair belongs to R. It is the definition of a reflexive, so R is reflexive. The relation R defined by is reflexive. Test for symmetry. A B order pair belongs to R implies and implied by A minus of B is equal to K. K means K is an integer. K belongs to Z set. That implies B minus A is equal to minus K belongs to Z set. The difference is an integer, which implies BA order pair belongs to R. Now we have a B order pair belongs to R. That implies BA order pair belongs to R. It is the definition of a symmetric. So R is symmetric. R is reflexive, R is symmetric. The first two conditions are satisfied. Test for transitive. ABC belongs to real set. AB order pair belongs to R and BC order pair belongs to R. AB order pair belongs to R implies and implied by AB order pair belongs to R implies and implied by A minus B is an integer. Implies and implied by A minus B is equal to K1 and B minus C is equal to K2, where K1, K2 belongs to Z set. That means set of integer, which implies A minus B plus B minus C is equal to k1 plus k2 is equal to k3. Sum of two integers is another integer belongs to z. Clear? Which implies this. B minus B and B can minus B cancel. A minus C is equal to K3 belongs to Z set. Which implies this. The difference of A and C belongs to Z. So AC belongs to AC order pair belongs to R. Now we have AB order pair belongs to R, BC order pair belongs to R, that implies AC order pair belongs to R. It is the definition of a transitive. So R is the transitive. R is the reflexive, R is the symmetric, R is the transitive. In general, R is an equivalence relation on real set R. Clear? First we have to test R is an equivalency relation or not. Since R is reflexive, symmetric and transitive, in general we can say R is an equivalency relation on X. Now we have to test, we have to find out the equivalent class. What is equivalent class? Equivalence class. A belongs to real set. It is defined equivalent class of A, or which is same as equivalent class of A for the equivalency relation R is defined by is the collection of X such that A belongs to real set equivalent class of A, or equivalent class of A for the equivalency relation R is the collection of X such that AX belongs to R, where R is the equivalence relation. We have to find out the equivalent class of 1. R is the equivalence relation. We have to find out the equivalent class of 1. A is equal to 1. So equivalent class of 1 or equivalent class of 1 for the equivalence relation is the collection of X. AX order pair belongs to R. What is the meaning of this? R is an equivalence relation. At what condition? The difference is divisible by, the difference is an integer. We have to find out the values of X so that A and here A is equal to 1. A is equal to 1. 1x. The difference must be an integer. The difference must be an integer. What are the values of X? A is 1. If X is 0, 1 minus 0 is an integer. If X is equal to 1, 1 minus 1 is an integer. If x is equal to 2, 1 minus 2 is an integer, dot dot. If x is equal to minus 1, 1 minus of minus 1, that is 2, is an integer. Similarly, minus 2, minus 3, dot dot. These are the collection of x values when a is equal to 1. Since a x order pair belongs to R, that means the difference of a and x is an integer, which is same as z set. That means set of integers. So equivalent class of 1 is equal to z set. That is set of integers. Second, a is equal to half. A is equal to half. So equivalent class of half, or which is same as equivalent class of half for the equivalence relation R. What are the values of x? So that the difference a is equal to half. What are the values of x? So that the difference will be an integer. Half minus 0. Half. A is half. Half minus 0. It is half plus 0. This minus this is an integer. Half plus 0 minus 1. Half equal to 0. Half plus 1 minus half. A minus b is an integer. Half plus 2. This minus this is an integer, or this minus this is an integer. Dot dot. Half minus 1. Half minus 2. Half minus 1 minus half is an integer, or this minus this is an integer. This minus this is an integer, which is same as collection of n plus half, so that n belongs to z set. N equal to 0, n is equal to 1, n is equal to 2, n is equal to minus 1, n is equal to minus 2, dot dot. The difference, this minus this is 0, this minus this, that is minus 1, this minus this, that is minus 2, this minus this, that is plus 1, this minus this is plus 2. So the difference is an integer. A minus x belongs to R. That means a and x are related. What type of relation? The difference between a and x is an integer. Clear? Therefore, equivalent class of half is equal to collection of n plus half, so that n belongs to z set. Clear? Clear? Here x is equal to n plus half. The difference and a is equal to half. X is equal to n plus, here x is equal to, here x is equal to n plus half. n belongs to z. N belongs to z. Here x is equal to n plus half. X n belongs to z set. Clear? Any doubt? Any doubt? Okay. No doubt? Next question. Suppose a box contains a set of n balls, n greater than equal to 4, denoted by B, of 4 different colors, may have different sizes, that is red, blue, green and yellow, so that a relation capital R defined on capital B as R is equal to set of B1, B2 order pair, so that balls B1 and B2 have the same color, is an equivalence relation on B. How many equivalence classes can you find with respect to R? The box contains the balls of different colors, red, blue, green and yellow. The relation R on B is defined by R is equal to set of B1, B2 order pair, so that balls B1 and B2 have the same color. We have to show R is an equivalence relation on B. Giving the relation capital R on B is defined by giving the relation capital R on B is defined by R is equal to set of B1 B2 order pair, so that balls B1 and B2 have the same color, where the box B contains balls of different colors, that is red, blue, green and yellow. The relation capital R on B is defined by R is equal to set of B1 B2 order pair, so that balls B1 and B2 have the same color, where the box B contains balls of different colors, that is red, blue, green and yellow. To show R is an equivalence relation on B. We have to test the relation R is an equivalence relation on B. That means R satisfies the definition of reflexive, symmetric and transitive. Test for reflexive. Let B1, B2, B3 belongs to B. Test for reflexive. For all B1 belongs to B, ball B1 is same color as B1. Ball B1 is the same color as B1. Is true. That means B1 and B1 are same color. Ball B1 is the same color as B1 is true. Implies B1 B2 order pair belongs to B1 B1. Belongs to R. For all B1 belongs to B, B1 B1 order pair belongs to R. It is the definition of reflexive. Therefore, R is a reflexive relation. Clear? It is the definition of a reflexive. That is, for all B1 belongs to B, B1 B1 order pair belongs to R. So R is a reflexive relation, symmetric. Test for the symmetric relation. B1 B2 order pair belongs to R, so that balls B1 and B2 have the same color. That implies balls B2 and B1 have the same color. Is true. B1 and B2 have the same color. It is given, which implies this B2 and B1 have the same color. Which implies this B2 B1 order pair belongs to R. Now we have B1 B2 order pair belongs to R. That implies B2 B1 order pair belongs to R. It is the definition of symmetry. XY order pair belongs to R. That implies YX order pair belongs to R. That is B1 B2 order pair belongs to R. That implies B2 B1 order pair belongs to R. It is the definition of symmetric. Therefore, R is symmetric. Test for transitive. Test for transitive. B1 B2 order pair belongs to R and B2, B3 order pair belongs to R. So that balls B1 and B2 have the same color. B1, B2 belongs to R, so that balls B1 and B2 have the same color. And B2, B3 belongs to R. Balls B2 and B3 have the same color. B1 and B2 have the same color, and B2, B3 have the same color. Implies B1 and B3 have the same color. Since B1 and B2 have the same color, B2, B3 have the same color. B2 is common, so B1 and B3 have the same color. Implies balls B1 and B3 have the same color, which implies B1, B3 order pair belongs to R. Now we have B1, B2 belongs to R. We have B1, B2 order pair belongs to R, and B2, B3 order pair belongs to R. That implies B1, B3 order pair belongs to R. It is the definition of XY belongs to R, YZ belongs to R, that implies XZ belongs to R. That here B1, B2 order pair belongs to R, B2, B3 order pair belongs to R, implies this B1, B3 order pair belongs to. So R is transitive. Clear? Since R is reflexive, symmetric and transitive, implies R is an equivalence relation on B. Hence proved. The first part is proved. Hence proved. The first part is proved. Here since R is reflexive, symmetric and transitive, implies R is an equivalence relation on B. Hence proved. Second part, how many equivalence classes can you find with respect to R? equivalence classes. A belongs to B, equivalence class of A. A belongs, it is defined by equivalent class of A, which is same as equivalent class of A for the equivalence relation R is the collection of X, so that A X belongs to R, where R is the equivalence relation. That means A related to X. That means there exists a relation called the equivalence relation between A and X. Equivalent class is a set. A and X are related by the equivalence relation. Let A be a ball of let A be a ball of any color. By definition, A may be red color or blue color or green color or yellow color. So equivalent class a red ball. A is taken as a red ball. Equivalent class of a red ball. Collection of X, so that A related to X. What type of relation? R is an equivalence relation. Here the relation is the same color. Same color is the equivalence relation. Then a red color is the set of X. A red color. What are the elements of X? That is a red ball. That is a red ball. A red ball and the set of a red ball. Equivalent class of a red ball is equal to set of. Here X is represent a red ball. Equivalent class of a red ball is the collection of or set of a red ball. Same color represent an equivalence relation. R is the equivalence relation on same color. If it is red color, it will be red color. If it is a blue color, it is a blue color. Similarly, collection A represent a red ball. What are the values of X? That is a red ball. Since same color represent an equivalence relation, A and X are related. Here R is the equivalence relation. That is the same color represent the equivalence relation. Similarly, a blue ball. Equivalent class of a blue ball is the collection of X. What is X? A blue ball. A green ball. Equivalent class is a set. Is the set of equivalent class of a green ball with the set of a green ball. Since same color represent an equivalence relation, and A equivalent class of A yellow ball is the set of a yellow ball. Equivalent class of a which same as equivalent class of a for the equivalency relation R is the collection of X so that A and X belongs to R, where R is the equivalency relation. Here R represents the same color. A and X are the A and ball A and X have the same color. So equivalent class of a yellow ball is equal to set of a yellow ball. 1, 2, 3 and 4 are 4 equivalent classes. Here how many equivalent classes can you find with respect to R? Therefore, the number of equivalence classes, therefore the number of equivalence classes with respect to R is taking red ball, you will get an equivalency relation. Taking blue ball, you will get an equivalency relation. Taking green ball, you will get an equivalency relation. Equivalent class. Taking a yellow ball, you will get an equivalence class. So the number of equivalence classes with respect to R is the equivalency relation is 4. Clear? Okay. Note down. Next question. Capital A be the set containing 1, 2, 3, 4 up to 9 and capital R be the relation in A cross A defined by AB order pair related to CD order pair if A plus D is equal to B plus C. For AB order pair, CD order pair belongs to A cross A. Prove that R is an equivalence relation. Also obtain the equivalence class of 2, 5 order pair. Given R is the equivalence relation in A cross A. Given R be the relation in A cross A defined by AB order pair related to CD order pair if A plus D is equal to B plus C. AB order pair related to CD order pair. AB order pair related to CD order pair. At what condition? The addition of A and D is the same as B plus C. If this condition is satisfied, AB order pair is related to CD order pair. R is the relation in A cross A defined by AB order pair related to CD order pair if A plus D is equal to B plus C. To show R is an equivalence relation in A cross A. To show R is an equivalency relation in A cross A. That means R satisfies the definition of replacive, symmetry and transitive. Let AB order pair, CD order pair, EF order pair belongs to A cross A, where A, B, C, D, E, F belongs to A. Cross product contains the order pair and a set contains the elements. To show R is an equivalency relation in A cross A. Test for reflexive. For all AB order pair belongs to A cross A. A plus B is the same as B plus A. A plus B is the same as B plus A. As A plus B is the same as B plus A. As addition is the commutative in subset of A subset of N. Addition is commutative in the set of natural numbers. Addition is commutative in A, that subset of N. Implies AB order pair related to AB order pair. A plus B is equal to B plus A. Clear? A plus B is equal to B plus A, since addition is commutative in A subset of N. AB order pair related to CD order pair if this condition is satisfied. A plus B is equal to B plus A. A plus B is this, so we can write this. Therefore, so for all AB belongs to A cross A, AB order pair related to AB order pair. Therefore, R is reflexive. X related to X. Clear? Clear? No doubt? Test for symmetric. AB order pair related to CD order pair. If A plus D is equal to B plus C, we have to show CD order pair. We have to show CD order pair related to AB order pair. That means C plus B, which implies this implies B plus C is equal to A plus D. We have to obtain this part. So the arrangement is C plus B is equal to C plus B. A plus D is equal to A plus D is equal to B plus C. A plus D is equal to B plus C. This condition implies this. B plus C is equal to A plus D. We have to find out CD is related to this. That is C plus B is equal to D plus A. This is same as this. Since addition is commutative in C plus B plus C is same as C plus B, A plus D is D plus A. Since addition is commutative. Since addition is commutative in A subset of N in the set of natural. Now we have that implies this. C plus B is equal to D plus A. So we can write CD order pair related to AB order pair. AB order pair related to now we have AB order pair related to CD order pair. That implies CD order pair related to AB order. Therefore, R is it is the definition of symmetry. It is the definition of symmetry. R is symmetry. Test for transitive. Test for transitive. AB order pair related to CD order pair and CD order pair related to EF order pair. So that A plus D is equal to B plus C. It is equation 1 and C plus F is equal to D plus E. Equation 2. It is equation 1. Equation 1 plus equation 2 implies A plus D plus C plus F. A plus D, here A plus D is equal to B plus C. C plus F is equal to D plus E. So A plus D plus C plus F is equal to B plus C plus D plus E. DD cancel, CC cancel. We have to find out dash. AB related to CD, CD related to EF. We have to find out AB related to AB order pair related to EF order pair, which implies this. We have to find out this term. A plus F is equal to B plus E. A plus F is equal to A plus F. It is B plus E. B plus E. A plus F. A plus F is equal to B plus E is present. This implies to this. Clear? A plus F we same as implies this. AB order pair related to F order pair. A plus F is equal to B plus E is present. A plus D is equal to B plus E. Then AB order pair related to CD order pair. Now we have AB order pair related to CD order pair and CD order pair related to EF order pair implies AB order pair related to EF order pair. Therefore, it is the definition of a transitive. It is the definition of a transitive. Therefore, R is transitive. X related to Y, Y related to Z, X related to Z. Here, AB order pair belongs to CD order pair. CD order pair related to EF order pair. That implies AB order pair related to EF order pair. Therefore, R is transitive. Since R is reflexive, symmetric, and transitive, implies R is an equivalence relation. R is an equivalence relation in across A. Hence proved. The first part is proved. Next, second part. Equivalence relation. R is an equivalence relation. Equivalence relation partitions or decomposes a given set into equivalence classes. Find the R is the equivalence relation. Equivalence relation decomposes or partitions the given set into disjoint equivalence classes. Equivalence classes. Equivalent class. Here it is only one element, that is a 2-5 order pair. Equivalent class of 2-5 order pair. Equivalent class of 2-5 order pair is defined as the collection of XY order pair such that 2-5 order pair related to XY order pair. Equivalent class of A is the collection of x, so that x related to a related to x. Here a is given by 2 5 order pair. A takes place 2 5 order pair with the collection of xy order pair, so that, and equivalent class of a is the collection of x, so that a related to x, where a is the equivalence relation. A is replaced by 2 5 order pair. Clear? Since here A is replaced by 2 5 order pair. Clear? 2 5 order pair related to xy order pair. AB order pair related to CD order pair. If A plus D. If 2 plus y is equal to 5 plus x. Clear? 2 plus y is equal to 5 plus 2 5 order pair related to xy order pair if this condition is satisfied. 2 plus y is equal to 5 plus x. Here x, it is y are the unknown quantities. X is equal to 1. 5 plus 1 equal to 6. 2 plus 4, that is 6. X is equal to 2. 5 plus 2, that is 7. 2 plus 5, that is 7. X equal to 3. 5 plus 3, that is 8. 2 plus 6 is equal to 8. X equal to 4. 5 plus 4, that is 9. 2 plus 7, that is equal to 9. X equal to 5. 5 plus 5, that is 10. 2 plus 8 is 10. X equal to 6. X equal to 6. 5 plus 6, that is 11. 2 plus 9, that is 11. X equal to 7. 5 plus 7, that is 12. And 10 plus 2 is 12. It is not true. Since the maximum of A contains 9. Here it is 10, it is not possible. So equivalent class of equivalent class of 2 5 order pair is the collection of xy, that is x equal to 1, 1 4, 2 5 order pair, 3 6 order pair, 4 7 order pair, 5 8 order pair, and 6 9 order pair. So equivalent class of 2 5 is set of 1 4 order pair, 2 5 order pair, 3 6 order pair, 4 7 order pair, 5 8 order pair, and 6 9 order pair. Clear? 1 4, 1 4, 2 5, 3 6, 3 6, 4 7, 5 8, and 6 9. It is not possible. The maximum value of the maximum of A contains, that is 9. Here it is 10. It is not possible. So equivalent class of this is this. Clear? Clear? Okay. Note down. Next, congruence modulo relation on integers. What is congruence modulo relation on integers? Definition: let AB belongs to Z set. That means set of integers and M be the fixed positive integer. A congruent to B modulo M is written as A congruence to B. This symbol is read as congruence. A congruence to B mod M. A congruent to B modulo M is written as A congruence to B mod M. This symbol is read as if and only if. That is if and only if or implied by M divides A minus B. Or we can say or A congruent to B modulo M is true when A minus B is divisible by M. A congruence to B modulo M is true when A minus B is divisible by M. For example, 100 congruence to 1 mod 11. That means 100 minus 1, that is 99, divisible by 11 is true. So we can write 100 congruence to 1 modulo 11. 7 congruence to minus 5 mod 3. That means 7 minus of minus 5, that is 12. 7 minus of minus 5, that is 12, is divisible by 3. So we can write 7 congruent to minus 5 modulo 3. Minus 20 congruent to 1 mod 7. That means minus 20 minus 1, that is minus 21 divisible by 7. Example 1. Example 2. Find two values of A and B so that A congruent to B mod 4. Find two values of A and B so that A congruent to B modulo 4. Answer. That means the difference is divisible by, the difference of A and B is divisible by 4. 3 congruent to minus 5. The difference is 8. A minus B mod M, that is 4, is true. Implies A is 3, B is equal to minus 5. 7 congruent to minus 7 congruent to 5 modulo mod 4 implies A is equal to minus 7, B is equal to 5. Minus 7 minus 5, that is minus 12 divisible by 4. So A is equal to 3 and A is equal to minus 7, B is equal to minus 5, B is equal to 5. Are two values of A and B. Clear? Clear? Okay. Note down. Next question. So that congruence modulo is an equivalency relation on the set of integers. We have to show congruence modulo relation is an equivalency relation on the set of integers. Let R be the relation on Z set. That means set of integers. Let R be the relation on Z defined by R is equal to set of AB out of pair so that A congruent to B mod the relation is defined by A congruent to B mod M. AB order pair belongs to R if this condition is satisfied. That means the difference of A and B divisible by M. To show R is an equivalence relation on Z. That means R satisfies the definition of reflexive, symmetric and transitive. Let ABC belongs to Z. Test for reflexive. R with the relation on Z defined by R is equal to set of AB order pair so that A congruent to B mod M. To show R is an equivalency relation on Z, let ABC belongs to Z. Test for reflexive. For all A belongs to Z, M divides 0. M divides 0. Is it true? That implies M divides A minus A, where A belongs to Z. For all A belongs to Z, that means A is any integer, which implies as M divides the difference of A and A. That means A congruent to A mod M. That implies A order pair belongs to R. Now we have for all A belongs to Z set, A order pair belongs to R. It is the definition of reflexive. Therefore, R is reflexive. AB order pair belongs to R if A congruent to B mod M, or AB congruent to B mod M. AB order pair belongs to R. Here A congruent to A mod M, that implies A order pair A and B are same. A order pair belongs to R. It is the definition of reflexive, so R is reflexive. Test for symmetric. Reflexive, symmetric and transitive. AB order pair belongs to R. AB order pair belongs to R. That implies that A congruent to B mod M. AB order pair belongs to R, so that A congruent to B mod M. That implies M divides A minus of B. That implies A minus of B by M is equal to K, where K belongs to Z set. Since A minus B is divisible by M, which implies B minus A by M is equal to minus K. Minus K belongs to Z, which implies M divides B minus A. That implies B congruent to A mod M. Clear? B divides, M divides B minus A. That implies B congruent to A mod M, which implies BA order pair belongs to R. Clear? AB order pair belongs to R, so that A congruent to B mod M. That implies M divides A minus B. That implies A minus B by M is equal to K. K belongs to Z. B minus A by M is equal to minus K. Minus K belongs to Z. That means M divides B minus A. That implies B congruent to A mod M. That implies BA order pair belongs to R. Now we have AB order pair belongs to R. That implies BA order pair belongs to R. It is the definition of symmetry. Therefore, R is symmetry. R is symmetry. Clear? It is the definition of symmetry. Test for transitive. AB order pair belongs to R and BC order pair belongs to R, so that AB order pair belongs to R, so that A congruent to B mod M. So that A congruent to B mod M and B congruent to C mod M. That implies A congruous to B mod M. What is the meaning of this? M divides A minus B. Okay. A minus B. And M divides B minus C. Good. M divides A minus B and M divides B minus C, which implies A minus B by M is equal to K1 and B minus C divided by M is equal to K2, where K1, K2 belongs to Z. K1, K2 belongs to Z. That implies A minus B is equal to M K1 and B minus C is equal to M K2. Clear? M divides A minus B, which is same as A minus B by M is equal to K1. M divides B minus C, which is same as B minus C divided by M is equal to K2. K1, K2 belongs to Z. Adding the above, which implies A minus B plus B minus C is equal to M K1 plus M K2, which is equal to M K1 plus K2 is equal to M K3, where K1 plus K2 is equal to K3 belongs to Z. BB cancel, which implies A minus C by is equal to M K3, which implies A minus C divided by M is equal to K3, which implies M divides A minus C, which implies A congruous to C mod M divides this, which implies AC order pair belongs to R. A congruous to B mod M, that implies AB order pair belongs to R. Here A congruous to C mod M, that implies AC order pair belongs to R. Clear? Okay. Now we have AB order pair belongs to R and BC order pair belongs to R. That implies AC order pair belongs to R. It is the definition of transitive. Therefore, R is transitive. Since R is reflexive, symmetric, and transitive, implies R is an equivalence relation on Z. Clear? R satisfies the condition of reflexive, R satisfies the condition of symmetric, R satisfies the definition of transitive. Since R is reflexive, symmetric and transitive, implies R is an equivalence relation on Z. The relation which is reflexive, symmetric and transitive is called an equivalence relation. We have to show congruence modulo is an equivalence relation. Therefore, hence proved. Clear? Clear? Okay. Note down. Next, division of algorithm. What is division of algorithm? Let AB belongs to Z set. That means Z is the set of integers. When A is divided by B mod of B. When A is divided by mod B, then there exist two integers Q and R, so that first condition A is equal to BQ plus R. Second condition R greater than or equal to 0, less than mod of B. Let A B belongs to Z. When A is divided by mod of B, then there exist two integers Q and R, so that A is equal to BQ plus R. R greater than or equal to 0, less than mod of B. A is divided by B. The quotient is Q. It is BQ. A minus BQ is equal to R. R is the remainder. Q is the quotient. R is the remainder. So A is equal to BQ plus R is the first condition. And the second condition is R greater than 0 or equal to 0, less than mod of B. If these two conditions are satisfied, then the division is true, otherwise false. The first condition implies that is A is equal to B plus BQ plus R, which implies A minus R is equal to BQ, which implies A minus R by B is equal to Q, where Q is an integer, which implies B divides A minus R. The quotient is Q, which implies A congruent to R mod. Since B divides A minus R, implies A congruent to R modulo B, which implies A belongs to equivalent class of R mod of B. Since equivalent class of R is the collection of A, so that A congruent to R mod, it is the definition of equivalent class, or we can say the collection of A, so that A related to R, where R is the equivalency relation. Here R is the congruence relation. Congruence relation or equivalency relation decomposes the given set into disjoint equivalence classes. So we can write A congruence to R modulo B, that implies A belongs to equivalent class of R. Since equivalent class of R is the collection of A, so that A congruence to R modulo B. Or we can write equivalent class is equal to A, so that A related to R, where R is the equivalency relation. Clear? Clear? Okay. Example. Find R. 35 belongs to equivalent class of R. Note, first note. A belongs to equivalent class of R modulo B. What is the meaning of this? Here R is the remainder. When B divides A, the remainder is R. A is equal to BQ plus R. Q is the quotient. R is the remainder. A is divided by B. This implies A belongs to equivalent class of R modulo B. Implies R is the remainder obtained when A is divided by mod B. This expression implies R is the remainder obtained when A is divided by mod of B. Now we have to find out R. First, 35 belongs to equivalent class of R. Eight. That means mod B is equal to 8. We have to find out the value of R. This implies R is the remainder obtained when 35 is divided by 8 and satisfying these two conditions. 35 is divided by 8. $35 is equal to 8 into 4 plus 3. The first condition is satisfied. And R is equal to 3. It is the remainder greater than 0. The second condition implies R is greater than 0 or equal to 0. Here R is equal to 3 greater than 0. Less than mod of B. B means mod of B means mod of B, that is equal to 8. R is less than mod of B. Satisfying these two conditions implies R is equal to 3 is the remainder. Clear? Second example. First example. 17 belongs to equivalent class of R 3. Find R. We have to find out the value of R when 17 is divided by 3. The question is 5. It is 15. 2 is the remainder. 17 belongs to equal class of R modulo 3 implies R is equal to 2. Since 17 is equal to 3 into 5 plus 2, the first condition is satisfied. 17 is equal to 3 into 5 plus 2. The second condition, R is equal to 2 greater than 0. Any one of the conditions must be satisfied from 2. R greater than 0 or R greater than 0 or equal to 0 less than mod of B. Mod of B means that is equal to 3. So it satisfies the two conditions. Therefore R is equal to 2. Here R is equal to 3. Clear? Next example 3. Minus 12 belongs to equal class of R 13. Minus 12 is divided by 13. What is the remainder? That is R. 13. Minus 1 which gives minus 13. 1 is the remainder. Minus 12 is equal to 13 into minus 1 plus 1. That is equal to minus 12. The second condition, R is equal to 1 greater than 0. All two conditions are satisfied. Implies R is equal to 1. Clear? Clear? Okay. Note down. Next, properties of congruence modular relation. Let ABCD belongs to Z set. That means ABCD are the integers and M is a fixed positive integer. First bit A congruence to B modulo M, that implies A plus X congruence to B plus X where X belongs to Z set. Second bit A congruence to B modulo M and C congruence to D modulo M. That implies A plus C congruence to B plus D and SC congruence to BD modulo M. Proof. First, A congruence to B mod M. By the definition of a congruence modulo, that implies M divides A minus B. Here, which implies M divides A plus X minus B plus X. X is cancelled, which implies M divides A plus X minus B plus X. Implies A plus X congruence to B plus X mod M, where X is an integer, may be positive or negative. The first part is proved. Proof. Second part. Second, A congruence to B mod M. A congruence to B mod M and C congruence to D mod M, which implies M divides A minus B and M divides C minus D which implies this A minus B by M is equal to K and K1 C minus D divided by M is equal to K2. K1, K2 belongs to Z set. Since M divides A minus B, we can write A minus B by M is equal to K1 C congruence to D modulo M. So M divides C minus D, that is C minus D divided by M is equal to K2. We have to show A plus C congruence to B plus D. Implies this A minus B is equal to M K1 and C minus D is equal to M K2, which implies this A minus B plus C minus D is equal to Mk1 plus Mk2, which implies this A plus C minus B plus D is equal to Mk1 plus K2, which is equal to Mk3. K1 plus K2. K1, K2 are two integers. Sum of two integers is another integer, that is K3 belongs to Z set, which implies this A plus C minus B plus D is equal to Mk3, which implies this A plus C minus B plus D by M is equal to K3. K3 is an integer. Implies this M divides A plus C minus B plus D, which implies this M divides A plus C minus B plus D, which implies this A plus C congruence to B plus D mod M. A plus C is congruence to B plus D modulo M, mod M. Second bit, next we have to show SC congruence to BD modulo M. Let it is star. Star implies this A minus B is equal to Mk1 and C minus D is equal to Mk2. From star, we have to show SC congruence to BD, which implies this multiplying C SC minus BC is equal to MCK1, multiplying B, we have to find out BD, BC minus BD multiplying B both the sides, which is equal to MBK2. Clear? Here multiply C both the sides, here multiply B both the sides, which implies this SC minus BC plus BC minus BD is equal to MC K1 plus M B K2. BC cancel, which implies this. SC minus BD is equal to M C K1 B K2, which is equal to M into K4, where CK1 plus BK2 is equal to K4 belongs to Z set. Clear? Since K1, K2, B and C are the integers, which implies SC minus BD is equal to MK4, which implies SC minus BD by M is equal to K4, which implies M divides SC minus BD, which implies SC congruent to BD mod M. SC congruent to BD mod M. It is a mod of M. Mod M. Clear? A congruent to B mod M, C congruent to D mod M, that implies A plus C congruent to B plus D mod M, SC congruent to BD mod M. The first part is A plus C congruent to B plus D mod M. In second part, SC congruent to BD. Clear? Clear? Next, example of the following properties. Example of first. Thirteen congruent to 5. 13 minus 5, that is 8, divisible by 4. A congruent to B mod M. A is 13, B is 5, modulo 4. 13 minus 5 divisible by 4 is true. A plus X congruent to B plus X implies yes. 13 plus 3 congruent to 5 plus 3 mod of 4. Since 13 plus 3, that is equal to 16, congruent to 8 mod 4. 16 minus 8, that is equal to 8 divisible by 4 is true. Clear? Clear? Here X is equal to 3. 20 congruent to 5 modulo 3. 20 minus 5, that is 15, divisible by 3 is true. Implies 20 minus 6 congruent to 5 minus 6. Here X is equal to minus 6. Mod 3, which implies 14 congruent to minus 1 mod 3 is true, since 15 minus 1, that is equal to 15 divisible by 3 is true. This and this are the example of 1. Second, A congruent to B mod M. Second example. Nine congruence to -6 mod 5. A congruence to mod 5 and 7 congruence to mod m congruence to 2 mod 5. M is 5. 9 minus of -6 that is equal to 15. 15 divisible by 5. 7 minus of 2 that is 5 divisible by 5. Both are true. We have to show A plus C. First and first, which implies this. 9 plus 7 is equal to -6 plus 2 mod 5. Implies this. 16 congruence to -4 mod 5 is true or false? 16 minus of -4 that is equal to 20 divisible by 5 is true. So the first part is true. Second part. SC congruence to BD mod M. It is A, it is C. 9 into 7 is equal to -6 into 2. 9 into 7 congruence to -6 into 2 mod 5 is true or false? That is 63 congruence to -12 mod 5. 63 minus of -12 that is equal to 63 minus of -12 that is 75 divisible by 5 is true. Clear? Is it 63 congruence to -12 is 63 minus of -12 that is 75 divisible by 5 is true. So the second part is also true. Clear? Next example. Example 3. 100 congruence to 1 mod 100 minus 1 that is 99 mod 11 is true. Clear? 100 congruence to 1 mod 11 is true. Dividing 100 by 11 that is 1. The remainder is 1. 100 can be replaced by 1 which implies this. 1 congruence to 1 mod 11 is also true. Another example. 23 congruence to 5 mod 9. 23 minus 5 that is 18 mod 5. Dividing 23 by 9, what is the remainder? That is 5. 23 can be replaced by 5 which implies this. 5 congruence to 5 mod 9 also true. 5 minus 5 that is 0. Divisible by 9. Another example. 75 congruent to 15. The difference is 60. Mod 12. 75 minus 15 that is equal to 60. 60 is divisible by 12. Dividing 75 by 12. 75 dividing 70 by 12. The remainder is 3. So 75 can be replaced by 3, which implies 3 congruent to 12. Mod 12. 3 minus 12 divisible by 3 minus 12, that is minus 3 minus 15. 3 minus 15, that is equal to minus 12 divisible by 12 is also true. Next, 75 congruent to 15 mod 12. Dividing 15 and 75 both at a time. 12 is equal to 3. 75 is divided by 12 gives the remainder 3, which implies 3 congruent to dividing 15 by 12, the remainder is also 3 mod 12 is also true. 3 minus 3 that is equal to 0 divisible by 12. Clear? These are the examples of the following properties. Clear? Okay. Note down. Next example. Find the least non-negative integer r so that 7 into 13 into 23 into 413 congruent to r modulo 11. R is the remainder can be obtained using these properties. That is A congruent to B mod M and C congruent to D mod M, that implies AC congruent to BD mod M. 7 into 13 that is equal to 91. Dividing 19 by 11. The remainder is G3. Implies 91 congruent to 3 mod 11. It is 1. 23 is divided by 11. The quotient is 2. The remainder is 1. Implies 23 congruent to 1 mod 11. True. Next, 413 divided by 11. Percentage is 3, 8, 7, it is 6. Implies this 413 congruence to remainder is 6 modulo 11. Now we have A congruence to B, it is equation 3. A congruence to B modulo M and C congruence to D modulo M, that implies AC congruence to BD. The left hand side is multiplied and the right hand side is also multiplied. From equation 1 and 1, 2 and 3 by the properties. By the properties we have from equation 1, 2 and 3 by the properties this we get 91 into 23 into 413 congruence to the right hand side is 3 into 1 into 6. 3 into 1 into 6 mod 11. By these properties, which implies this 7 into 13 into 91 can be written 7 into 13 into 23 into 413. The right hand side is 18 congruence to 18 is divided by 11, quotient is 1, it is 7. Mod 11. It is equivalent to, but 7 into 13 into 23 into 413 congruence to R mod it is 4, it is suppose 5. Comparing 4 and 5, we get R is replaced by 7. R is equal to 7. Clear? It is the application of this properties. Okay, no doubt.